We're here. I hope you had a really great lunch. Now I know we've had a lot of people asking about all the hardware after our introduction about the software. So we're going to have John and John, but not Astra, come and tell you all about the decisions that went into making the badge and a little bit of ear licking and a little bit of information about all the SAOs that go on top. So without further ado, I present to you John and John.
Hello everyone. Seamless transfer there from seat to seat.
Seamless. No
Seamless. So, my name's John Spencer, and those of you who've been in open hardware mini-comps before will recognise me as giving fairly rambling talks, normally way too fast. John has asked me to slow it down today, so we'll see how that goes. So, I'll get right into it and start talking about our hardware. So, this is the putting the swag into the badge talk, so to speak. And I've lost focus. So, I'm going to start with a bit of a history lesson of open hardware miniconf badges. Way back in 2017 was when we first really started looking at badges. It was a different time. We were doing it in preparation for the Sydney LinuxConf. We rushed through a few designs. We approached Linux Australia to see if they were interested, which they were, and that was all good, but there was problems. We got to like the third iteration of the hardware to see if it was going to work, what it was going to take to get it manufactured and out to people was very, very tight. And our budget available was way too tight, it just really wasn't going to be possible. And lastly, of course, if we did that badge, we had no chances of doing a regular project. Those of you who remember, the project for Sydney was the Lowland, the Lollybot, so the little, the soccer playing bot. But we did design something which I was calling the minimum viable badge. Now the first thing to note about it is there's not very much that's minimum about it. It used an e-paper screen, and it had, I think it was close to 30 different pieces on it, which is more work for us to produce. We would have had to get it done in China, that sort of thing. But the prototype was sitting there and sitting on shelves. I think John's hunting around for it at the moment, maybe. There's a few prototypes floating about. So we shelved that. Fast forward 3 years later, and 2020 has a whole new ball game of stuff. Obviously, we can't go to Canberra, which is a bit sad. My first LinuxConf was in Canberra, and I was kind of looking forward to going again. But obviously, someone from the organising committee remembered that we'd done this badge thing before, and sort of said, well, look, we'd like to do something special for everyone, even though they can't get anywhere. We'd like to give them some hardware. And here's your budget, which, yeah, that's not a bad budget. Obviously, it included postage, which was a bit fun. There's a request to make about 300 of them. I don't think we'd quite got to 300. I think there's a few failed sitting around.
We're at about 294.
294, that's actually pretty good. That's not a bad yield, except for the fact that there's a whole row of PCBs that are wrong. And the intention there was to get them to people before the conference, which is also a challenge because shipping is fun. In 2020, shipping was really fun. We also had to design and build and test and do all of the fun things that you do with hardware design in isolation. We had weekly meetups and weekly catch-ups, but still, it was very much on our own. As I'm going through, like we did have some challenges, as I just mentioned. We did a first version of the board, and someone, me, accidentally used a different OLED to the one we ordered. So the ground and the 5-volt lines were back to front, which, if anyone is interested, that means that things get hot and things don't go well. It definitely wasn't happy. John did hack a few of them to get them working so we could start working with real hardware, but we have a box of them here.
Here is a box of PCBs.
Yes. It's embarrassing.
I think it's about 5 kilos of PCBs.
Right.
Version 1.
That caused us small problems. Something else that you might not be aware of, about a week before we were due to start John was due to start shipping them out, we discovered that the lanyards changed our postal rating. So this was a question that someone asked me earlier today, is why we didn't ship with batteries. The original intention to keep our budget right down was to ship the badges as letters. They meet the minimum size restrictions, they're thin, they don't have any dangerous goods on them. That plan changed very rapidly when we found that the lanyard battery badge section made the package too thick. So we had to completely change that. Great expense. Yep, great expense.
Yep.
But very last minute. There's also obviously concerns with if we could have done some, people who are willing to pay more, we could have done something like that, but that adds a great deal of extra complexity. You're managing multiple shipping trains rather than a single one. So you can find your own batteries, they're not hard, I'm sorry. Now, of course, big thanks there to the LCA 2021 organising team. They were super helpful, and I'm quite happy to step in and help when things got a bit much. So, the pitch. Obviously, when we first started talking about this, the badge I showed from 2017 just wasn't going to cut it. The e-paper is still amazingly expensive. It's difficult. There's no nice modules, or there are nice modules, but they are expensive. So that would have ended up with an awful lot of build, an awful lot of time taken to either build them here or get them done overseas. So one of the projects that John had been looking at is a thing called FreeDeck. Now, FreeDeck runs on a Arduino Nano, or Pro Mini, Micro instead, rather. It has 6 screens, as you can see. It uses I think, a shift register to try and access the different screens on a single I2C bus, and a few other little bits and pieces like that. Much as with our badges, there's a button underneath each one of those. So we wanted to do something like that, but we wanted it to be simpler, faster, and of course with better access to the internet. So the first most important thing once you've decided what you're doing is the name, I mean the microcontroller. If you don't know the name, you don't know what it's going to be, do you? So there are a lot of options for microcontrollers out at the moment. The ATmega32U4 is a good choice because it offers a human interface bus control. It can be a mouse or a keyboard. STM32, I think it's M0s are quite popular. I think John uses them for a lot of stuff. They're also very, very cheap. The ESP32 S2 is another option, which can be a human interface device. And of course the Raspberry Pi Nano, which is a great looking thing, and if we had a time machine, is probably a real contender. Unfortunately, it was literally released while I was writing these slides. So we didn't go with any of those ones. We picked one called the Lowland 32 ESP32. A big driver for that is it costs literally $3 per unit, which when your budget's only $20 makes it possible. Much like the S2, it's a 240 megahertz processor. It is dual core, but for the most part the first core is just used for Wi-Fi and Bluetooth. You can use the Bluetooth for HID if you want. I'm not sure if anyone's done that yet. And once again, it is $3, not $20. So here I just thought I'd talk a little bit about what exactly the ESP32 is. This is obviously a very brief introduction. It's low cost, it's low power, and it's a system on chip. It has quite a good stack of interfaces, I suppose, like Wi-Fi and Bluetooth, obviously. In the designs I've shown, or in the modules I've shown here, it's coupled with a few extra things, so like a USB bus, so that you can do USB communications or USB serial to it. It's Arduino compatible. If you're used to writing C in the Arduino language, it's MicroPython compatible, which is obviously what we're using for this project. and it's Lua RTOS compatible, which is something I've never written, but a lot of people do seem to like it. We've used it in a few previous miniconfs, so we're quite familiar with it. In Tasmania, we built the IOTUS using it. IOTUS was built with almost pre-release chips, actually. We got a special delivery of those. And then Sydney, the Lollybot that I mentioned before. There are multiple prototype boards that are available. We used the Lowland 32, or technically the Lowland 32 Lite. They have multiple variants. If you do a Google search, you will get them all, and they have different pinouts, which is very fun. There's the Tiny Pico and the Tiny Nano, made by Unexpected Maker. And Adafruit has their own Huzzah 32 as well. My general preference is the Tiny Pico. A lot of that's because they're a little bit more expensive, but Sion, who runs Unexpected Maker, literally lives the next suburb over from me, so delivery is really good. Now, to give you an idea on how big these are, I've included a banana for scale. These are small. The Tiny Pico is very small. Yeah, okay, can't find that slide. Next one. I'm going to jump straight into how we built this schematic. Now, I wouldn't normally go through these sort of details, but this is a simple design. Each board only has 5 physical components, and it's a good place to get started when you're designing with modules. Once again, we used KiCad for our design work. We've done that for a few years now. So, the first slide here is our... I've split this up into 3 different views, working from left to right. On the left side, we have a schematic view, which is where you draw out how you want your design to work, like what you want it to connect to. In the middle, we have what it looks like from a module view. And then at the end, I've got a picture of the actual physical thing we're doing. This is a terrible example. The way I laid out the Lowland 32 was very hacky and very last minute. You wouldn't normally organize it like that. Almost everything about it is kind of wrong. You'd normally, like, that representation is pretty much exactly the same as what the physical chip looks like, where normally you would organize it so your inputs and outputs and your voltage and your ground planes are different angles. So these are terrible examples. The same with the module view there in the middle. That's a very specific one for our project. It's upside down, which is not some way you would normally lay it out, and it includes some edge cuts. Still, that's what we were looking. That's what, if you load up KiCad and look at our source, that's what you will see. A little bit more of a summary for the Lowland 32. I wrote this slide before I wrote the previous one. It is cheap. It has a couple of extra features that some people have noticed already. It's got battery management on it. So you can just plug a battery in and it will start charging for you. It's got a regulator, nice. Has a USB serial chip and a little bit of circuitry that lets it flick that on when you go to reprogram it. That's good because that's like 6 or 7 extra components that if we just used the raw ESP32 we would have to add to the board. It's got a good number of pin breakouts. The one I always miss is 5 volt out from the USB, which the Tiny Pico does have, but the ESP doesn't. Also uses different I2C pins, which is always fun. I think I mentioned again, it's cheap. It's very cheap, but ultimately this is all less work for John. It did mean we needed to solder and cut 26 pins for each badge. So of the 296 badges, I had the maths up, but I can't see it because I don't have my slide notes here. That's a lot of cuts. Hundreds of thousands of cuts, I think I worked it out to be. Which Andrew Nielsen and I think did a lot of them, almost all of them I think. So the cuts I think were the worst. You build up a callus on your hand. So the next component we have is our OLEDs. Now these are underneath an inch OLEDs. They're very common. They're 4-pin because I2C only really needs, well, ground, voltage and SDA and SCL, like the clock and the data. We have 2 of them here and they're obviously on the same bus. So again, move from left to right, that's our schematic view. and where it connects back to the microcontroller. What it looks like inside our PCB design, and then a stock photo from the website we bought them from. These are great little OLEDs. They're very inexpensive. I think a couple of dollars each, $2 or $3 each again. Because they're an OLED, they're self-illuminating. They're not like an LCD, which is backlit. They're very simple to address and use, and because they're used in a lot of places, libraries are very easy to get. Unless you're doing things like Mark is and trying to push it to its nth degree, you can get a display fairly easily. This particular model you can have two displays on the same I2C bus by bridging a solder gap to get the alternative address. Now, we made 300 badges, so we had 600 of these. These had a lot of failures, a lot more than we would have expected. And ultimately, John had to bridge 300 pins to get the alternative I2C addresses. We offered to help, he did it anyway. They're also pre-soldered, which means we only needed to cut 4 pins for each badge rather than 8. Oh, sorry, solder 4 pins for each badge. The next component we have is the buttons. There are 2 buttons underneath each of them, or 1 under each LCD, or OLED rather. We made these in a dual footprint because we weren't sure what buttons we'd be able to get. John soldered all of these, and we did offer to help again, and once again he did it all himself. So those were the physical components. That was the last physical component. So yeah, a single microcontroller, 2 OLEDs, and 2 buttons as well. So yeah, there's only 5 physical components on each board. We have a few extra features. The ESP32, something I didn't mention when I was talking about it, is it has a touch sensor, or a capacitance touch ability on 8 of its pins. So we utilized 4 of them on the board itself. Now, this is something we originally designed. Actually, I'll talk about that in my next slide. Once again, schematic on the left-hand side there. This looks a little bit strange because we have the touch sliders, and then we broke out the touch points individually as well. If you flip the board over, underneath sort of where the touch sliders are, you'll see that there's individual points. Just made it easier. You can solder to them if you need to. And in the center, so this is a good example of where we've used solder mask to sort of hide some details. In the center, that's what the copper pore looks like on the PCB. Versus at the end, what it actually looks like on the physical process, you can't really see like the little fingers. So you sort of hide the detail a little bit. So these were good because there's no soldering. You just drop it in. In this case, the way we use them as a slider is it's a proportional measurement between the 2 main ones. As the surface area that you're hovering your finger over reduces, obviously you can get a proportional measurement between the 2 points. Originally this work, I sort of based my original designs on stuff Nick Moore did back in 2017. He did it with, it was just copper paint, paper, and some sticky tape. It did work in my original prototype, and then Andrew Nielsen went through and he cleaned it all right up and gave it that sort of iconic look with the 2 circles and the line between them. So good work there, I think. And the last sort of components we have is our SAO connectors. John's going to talk more about SAOs later. The protocol for these, or the standard, I guess, is you have ground, you have voltage, you have ground, you have your I2C bus, and you have a couple of I/O pins. Now, because the ESP32's got plenty of I/O pins, we were able to comfortably get 4 SAO pins on each one. You'll notice, this version I cleaned up, but if you actually load the schematic, you'll see that I've shuffled the numbers around a little bit in the column on the left-hand side there, and I'll talk to that as to why. Those badge connectors I've taken pictures of. The ones with the little lock in them are great. Good luck finding them. The other works just as well, but yes, the nice ones are very hard to get a hold of. Breakouts as well. When you've got extra pins, it's always nice to sort of have some other way of plugging into them. Sometimes you will need more than just the 2 GPIOs that you get available on a SAO, so they're here. These are great. We didn't have to solder anything for these ones. They're more for you to enjoy later. So that's talking about how the design worked, I guess, the schematic design. Now I'm going to try and talk about the sculpting of a PCB. Most of this was done by Andrew, so I'm a bit blunt with my designs. I'm sloppy and all of the things lazy people end up being when they're trying to design something. We decided on the size pretty early on because it had to fit in that letter package I mentioned. So we sort of took what the largest space we could fit into that letter was and fit all the components on it. But we only have 5 components, so that's fairly easy. KiCad still doesn't have particularly good drawing tools. I think Andrew used a lot of AutoCAD because he was a draftsman at one point and that's how he thinks, so that's fine. As long as you've got rounded corners though, everything. That's all design is as far as I can tell. So, placing your components. As I mentioned earlier, designing by components is a very good way to start because you're starting with something that you know already works or should theoretically already work. The first thing I normally say is try and put things near the edge when you begin with, because otherwise you end up with fun situations where you've got a USB stick in the middle or USB plug in the middle and you cannot work out how to get to it. We've run into that before where there was a screw right at the end of the USB. That was fairly silly. I like things that are symmetrical. Most humans do. KiCad has a thing called the rat nest, which is all of its lines indicating where all of the pins connect to other pins. It's before you draw your tracks. It's very confusing early on, so I suggest turning it off. And also, do your graphics last, because most of your design will end up, like if you've got large graphics, you won't be able to see anything else that you're working on. So, KiCad calls traces tracks. Either way, you can think of them as wires. You should be using thicker traces for voltages. You can work out exactly how thick, or you can just fudge it like I tend to do. You will find some that overlap here. Now, it's not really clear from this photo, but the reason why this particular trace, and that's the rat nest you can see there, the reason why it doesn't work is because, I don't know where my cursor is, this section, top section of the microcontroller is where the Wi-Fi antenna is, and you can't have any traces run behind that unless you're really, really, really desperate. So in order to run to that point over there, you'd have to run right around the top of the micro and up to them, which is possible, but one of the first things you'll find you're doing after you've got a layout that you like is reordering literally everything. So you'll find that you can do it 2 ways. Obviously, you can rotate and move components so that they make sense, or you can adjust where things are. You'll almost always find at least one pin that's on the wrong side of the microcontroller, and it's just a pain in the proverbial. And the next step I would normally go through is adding a ground plane or a voltage plane, or both, more often than not both. In KiCad, that's this little green button that's down the left-hand side of your screen. That lets you sort of flick between the views. The ground plane normally covers almost the entirety of the back of the board, and that's one of the reasons why Nicola gave you all those tips on why not to eat the board or drop it in water or stick it to a fridge, because that ground plane is exposed. And the reason it's a bit exposed is because of our logos and graphics. Now, this is another piece of Andrew's work. Normally when you're designing PCBs, you're a little bit limited to 2 colors for all your fancy bits. But we've cheated, which is also a fairly common thing to do these days, to get an extra color by removing what's called the solder mask, which is like the thick coating over the top of all of the wires so that they don't get damaged or shorted out. That's the bit that is the bit that you could probably easily sort of accidentally short. These are something else. Once again, graphics, KiCad are not the best of friends. You can use Inkscape, you can use anything you'd like to design a graphic, and KiCad is pretty good at importing JPEGs and putting them on layers. And I think that's the end of my half of the talk, so I'm going to hand over to John now, and he can cover SAOs.
Yes.
Thanks, John.
Fantastic. Thank you. Okay, this is our seamless speaker transition. You can't tell the difference. So the part of the idea of a badge is that the badge itself is something that you should be able to extend and experiment with. So you might want to add extra functionality, or maybe you want to add an extra bit of bling. You know, you need some decoration on your badge, or you need something plugged into it that is going to add some extra functionality. So you just need a little bit more, swagger in the badge. How do you add it? Well, that is what the simple add-on headers are for. The connections that John showed earlier are these 6-way headers, and as he said, there are 4 of them on the badge. We could fit 4 on, so we put 4 on. They provide I2C and digital connections and power, so if you want to use them purely for mechanical mounting, you can, or you can put in an extra circuit board and actually communicate with the onboard microcontroller on the badge. So this was a render of one of the first versions of the badge, and you'll see that the SAO headers are on 2 different alignments. The ones at the top are what you would expect in terms of the normal orientation, and then the ones on the side are vertical. So the SAO would stick out sideways. And we had a little bit of a debate early on about whether they should come out sideways or at an angle. So we drew some different diagrams, just sketched it around and see how they would fit. This is a version I did where I printed out a little expansion board and just physically placed it onto a printout of the badge so we could see whether it would obscure the screens, trying to get an idea of where those connectors could go. And as you can see on the final version of the design, the badges are at a 45-degree angle, so that add-ons that you add onto the side of the badge come out on the side like ears. So, question is, what can you do with them? In your package, if you received a Swagbadge, you will have received 3 add-ons. There are 2 which look like the render on the screen, and these are little prototyping expansions. The idea with this is that you don't need to design your own circuit board to add functionality to the badge. This is equivalent to a prototyping shield for an Arduino, except that it's for a badge. And the breakouts around the edge are for the power and I2C connections and the 2 digital pins. There are 2 of those in the package, one black, one red, just because we could. And there is also an add-on which looks like the little Tux, which is really, really cute. Now this one was intended not to have any specific functionality. It's a PCB, but it doesn't have any components on it. But then I think it was Andy realized very quickly that if you had this plugged into the correct port, what you could do is bridge across a solder jumper onto the copper of the badge, and you could turn Tux into a little touch sensor. So Tux can be, you can boop his snoot and the badge can detect it. So if you want to experiment with that, we can talk you through that on Spectrum, or there'll probably be some information on the wiki when the time comes. So the idea with these is that you can add extra functionality, and so this is an example of another SAO, which I think this one was designed by Andrew Nielsen, who also did the little Tux. We haven't had this one fabricated, but that's just an example of creating something that is visually interesting that adds something to the badge. So the idea is that you can use them to personalize the badge as well as add functionality. So if you have received the SAOs in your package and you're wondering what to do with them, what you can do is something like what I did here, where I added the mushroom. This is the red SAO, and it's got the pin soldered onto it, and all I did was blue tack a bit of paper onto it. So that's just adding a little bit of decoration onto my badge, and now I've got a mushroom on my Swagbadge to go along with the Swagger. And of course, you've got to look out for the snake, but we've already got Python in here, so the snake is taken care of. So I also designed a couple of others which we did not end up including in the package. We ended up settling for just doing the prototyping version. This is a screw connection simple add-on so that you can use a screwdriver to add wires in and make connections to the badge. And this one has very large holes in it which are designed to take alligator clips. So if you had alligator clips on jumper wires, what you could do is plug this into the badge and then clip onto the edges and make electrical connections. And this just gives you some idea of the different things that you can do with these add-ons. So if you want to go to the next level, you can do some things like what is seen here. These are both designed by John, and a couple of years ago John designed a solder training kit called the Solder Rocket, and he's now done a version of that which is in the form of a SAO. So on the left there you can see the Solder Rocket, and it's got an LED on the bottom instead of where the rocket thrust would come out, and it's got headers so that you can add it onto a badge and it can take power. Oh, there's an example right here. Fantastic, thank you. So you can see here, this is the little Solder Rocket version of the simple add-on. It's a bit bright there, it's blowing out the camera, but you can see that there's a green LED on the bottom, which is the drive, whatever the thrust is coming out of the back of that. What makes green? I don't know.
Awesome.
So if we switch back to the slides for a second, you can see the Solder Rocket, but you can also see the badge beats board on the right, and that is a series of stacked LED bar graphs. So you can use that as like a VU meter. So I think John hasn't got this one quite working yet. He was just working on this. But the idea with this is that you can have your badge react to something like sound level, and then you can have a VU meter displayed on your badge with dancing LEDs. Now, there is a term that you should look for if you're interested in this sort of thing, which is badge life. And that is a term that came out of DEF CON, which Nicola mentioned right at the start of the day, is really where this whole electronic conference badge phenomena originated. And badge life includes development of both custom badges, but also simple add-ons, or SAOs. And if you search for badge life, you'll find an amazing array of different badge designs, but also simple add-ons. And because, well, it's going too much to say this is a standard, but the simple add-on header is a convention, I suppose, a very loose convention. So if you take your LCA Swagbadge and you solder the connector on here, you can then plug in other simple add-ons. Now, one thing to note is that the first version of the simple add-on standard had 4 pins, not 6. And that was a little bit limited because it was basically just power and I2C. The standard was extended not all that long ago to add the extra 2 pins. So we're using the current version of the standard, which is the 6-pin version, but it is backward compatible with the 4-pin. It's just added the extra 2 pins on the end. So if you look at simple add-ons, you might find that some of them have 4 pins and some have 6, but it is backward compatible. So if you get a 4-pin simple add-on header, you can plug it into your Swagbadge and it will work as long as you plug it into the correct 4 pins. So pay attention to that. Oh, and also while I'm talking about pinouts, there is a trap. Because the convention for the pinout evolved over time, you'll see that there is a little marker next to pin 1. But it is not the pin 1 that is on a conventional pinout. So the result is that if you look on the Swagbadge, the add-ons that we included, they have a pin 1 marker on them, which does not align with pin 1 on this header. So don't let that trip you up. You just need to make sure that you put it in the correct way around and it'll be fine. ignore the dots. They will lead you astray. So there is a lot you can do to extend your Swagbadge and make it do different things, both in terms of modifying the software, as Nicola and Andy spoke about earlier, but also in terms of extending the hardware and adding your own features into it. So it's if you don't have much experience with electronics, this is a really good way to get started, because you can effectively think of your conference badge as a microcontroller development board. It's got the MCU on there, there is Wi-Fi, it's got USB so you can upload new code, run MicroPython on it, it's got displays, all the basics are there. And then with these headers, you can add your own bling, which could be as simple as adding some LEDs on a simple add-on header. So it's very easy to get started. So, thank you very much. And I think there were a couple of questions that might have been in the chat earlier. And Nicola, you had some questions.
Well, lads, why don't you come and join me here in front of the camera?
On paper, nonetheless.
I went old school to fit us all in. So Paul Schultz, he wanted to know, why are there holes next to the sliders? What are they there for? And now I know that there was some reasons, because I have indeed asked this question before. And there are good reasons, and I don't know what they are. Tell us.
My recollection was they were cable ties.
Cable ties.
Was it cable ties? If you solder something onto it, if you've got a cable tie around that, it gives you extra support.
Okay.
I can't remember. That was something Andrew put on.
No, I have my recollection of it. It might be one of those things where it's there and nobody knows why.
Well, part of it was mechanical stability.
Yes. There were some early concepts that involved add-ons on the sides that turned it into something like a game controller, so that you could hold it and use the touch sensors. And I think this was for mechanical mounting, so that you could... So if anybody out there has a 3D printer, what you could do is design and 3D print a handle that goes on each side and then screw it on through those holes. And then you can use this as a little game controller.
That's pretty cool. Trent Lloyd was asking about the charging LED on the back. So when you put in either power or a battery, that LED on the back there can flash or shine in different ways. And maybe it's a bit non-intuitive. We've all discussed in the chat room how what it does is in fact standard.
Yes.
But it does, the little pinout on the board says charging. So what does it mean when it's flashing? What does it mean when it's steady on? I think Andy might know this one.
Okay.
Yeah, flashing is nothing's connected. Solid is charging and it goes off when it's charged.
Okay.
Awesome. And Paul Schultz again was asking about pins or sockets on the badge, and for the posterity, maybe we can give the answer in the video.
Pins or sockets? Sorry.
Yeah, so for the SAO, sorry.
The standard on the standard on the badge is the socket.
Yes.
So that your badge doesn't stab you.
Yes.
As a general rule.
Also, so you're not exposing power and ground on a pin.
Yes.
Yes.
And then the add-on has the pins on the back. Now, one thing that is an interesting little offshoot of this is chasing a squirrel, which I've been known to do once or twice. So the idea is that SAOs became an add-on for badges. But SAOs themselves have become so amazing and so elaborate that they are an artwork in their own right, and some of them are very complex. So it is now actually possible to buy desk stands which are SAO trees, and all it is a row of SAO sockets, sometimes at different angles, which provide power, and a desk stand so that you can plug your add-ons into it and have them displayed on your desk and powered up.
That was a pretty good squirrel.
It's a great squirrel. Right, there's no kind of further questions from the chat, although I'll be continuing to monitor. But, if you guys would like to talk a little bit more maybe about some of the additional projects that we came up with that we didn't have time to finish. So, you mentioned the game controller that I know Andrew was looking at. I've looked at building wings for my badge that would flap using electrically conductive wire. What are some of our other cunning plans that we have that we would like people to do with their SAOs?
I think I made mine.
Well, one that I had in mind, which I didn't get to, was making a SAO which represented a heart, and then have that linked to a heart rate monitor so that it would show heartbeat in real time on the badge. I think that would be a cool thing to do. Also, one thing that we talked about, in fact Nicola and I talked about, was having some kind of a solenoid-based party popper activation system so that we could have people send messages to our badges and have it let off a party popper, which could give you a bit of a shock if you're not expecting it.
I did have one. My solder rocket has a three footprints on it, or three uses. One of which is the tiny Pico Nano, once again from Unexpected Maker. So I thought it would be cool if you had 4 solder rockets with tiny Picos on them, and the base one, you'd have 10 cores on a single badge.
Ooh, imagine a Beowulf
Wouldn't be
cluster of
helpful,
those.
but still, it would be cool.
No, not very helpful. Yeah, are there any other questions coming from the chat?
Trent's asking for a little bit more information about the pin 1 thing. He says the pin 1 spot on his red and black board seems to be in the same place as the badge.
Yes.
So is there
Okay.
a way to confirm visual?
Yes.
It should have linked to the standard documentation. Documentation.
All right, I will try to get this up close to the camera where you can see it. If you're looking at the front of the badge, and we'll use this header as an example, you can see that there is a dot up there signifying the orientation. Now I'm holding the SAO in the same position, and unfortunately this is going to be very small on your screen, but the dot is not in the same position. This is oriented to plug directly in, but the dot is actually on the bottom near this pin here, when it should be up near this pin here. So in order to avoid confusion, because the SAO protos look identical on the two sides, it's very easy to get them back to front. What I did was put text on the back that says pins this side. So the general rule is if you put the pins on the side where it tells you to, and you plug it in, it'll be correct. So ignore the dot, just follow the pins.
And then someone was also asking about, I've lost the question because I'm very clever like that. Maybe it vanished. I don't know. Oh, the pads. Pads like 015/T3. What are they for?
So it's probably easiest to go backwards for that one. The T indicates it's a touch pad. So it has the ability to be the
Can
capacitive
you maybe
touch.
show people where this is on the back of the badge?
I'm just seeing if we've got a diagram of it with the pin out in the slides anywhere. I suspect we don't.
That does sound like the sort of useful information I would have not included.
Okay, now this slide here, actually yes, we are going to try something. We're going to try something dangerous here, and I'm going to switch to a different camera. So we are now looking at the overhead camera. Yes, and
I'll flick that over.
flip it over. You'll see some little notes next to the pin connections. Now, as John was saying, the T indicates a touch input.
So here's some T's. There's T's down this row here.
So you can see very small text on there.
And some over here as well.
So in the code, when you are referencing the touch inputs, you can use those. That helps you understand which of the touch channels is associated with the pins.
I believe it's just an alias. I think you can
I
still
think
use
you
an
can
IO,
reference them directly.
IO reference as well.
Yes.
Interesting, in Arduino, 2 of them are back to front.
Oh, that's not good.
Yeah, 8 and 9 are referenced backwards.
Discovered the hard way.
I did.
All right. I don't know if we answered that question.
We answered a question.
Trent wanted to know what the T indicated. So there are some A's. Okay, so there are 3 different types of label on the pins there. Well, actually 4. The A series shows the ADC, which is analog to digital converter. You can see there is a DAC, the DAC, that's digital to analog converter. You can also see the T numbers, those are the touch channels. If it says PWM next to it, then it is capable of PWM output, so simulating an analog voltage. And the final number next to the pin is the direct I/O pin number, like IO27, IO32, etc. Now, one thing we haven't mentioned yet is that you will see that some of them have a black border around them. That border indicates that the pin is in use by one of the other headers, like one of the SAO headers. So you need to be careful when you are picking which pins to use to not conflict with something that's already in use. If you have a SAO that's plugged into one of the other headers, it might be using IO4, for example, then you should not use that for something else at the same time. And I think we are pretty much out of time now, so we are now going to wrap up, and Nicola is going to do her MC duties.
I sure am. Thank you very much, John and John. As you know, we'll all be hanging out in the BOF session, and you can catch us on Spectrum if you've got further questions. But for now, take a break, stretch your legs, don't forget to grab a drink of water, and we'll be back soon for a killer talk about FPGAs.
Yes, I'm excited about this one.
I think we're all looking forward to that one, actually.
See you soon.